Today's lecture is going to be on the moon, and we are going to look at moon characteristics and features. We will compare or contrast kind of the concept of what tidally locked, what that actually means. We'll look at the lunar surface, interior, and composition. We will take a look at the surface features that provide the storyline of the primitive solar system bombardment period, which we call the Hadean, which took place within the Pre-Cambrian. We'll view surface features of the moon and name them. We'll discuss how a crater forms, and we'll do some simple relative age dating of lunar surface features. So here goes. So, do we actually only see the same side of the moon? Well, yes, actually. It's because the Earth-Moon is tidally locked that the orbital period, right, of the moon, take a look at the green coloration of the picture, the time for one orbit, equals the moon's rotational period, or the time to turn 360 degrees. We look at the picture above that an Earth observer will never view the green shaded area, the far side of the moon. Because the moon has a 1-to-1 ratio, right, a 1 rotation to 1 revolution, this leads to the moon being tidally locked. We only see the same side of the moon. We never see the far side of the moon. So let's go back to the Pre-Cambrian to now. And this is kind of we're going to go back in time during the heavy bombardment period, the Hadean bombardment. That as the Earth was experiencing heavy bombardment, so too was the moon. The primary difference as to why the moon still has cratered surface is simple. It has no atmosphere for the water cycle. So no weathering of erosion is erasing these bombarded paths. So it still remains today. So check out this video. You can do that on your own. This just kind of talks you through the different phases, particularly early during the bombardment phase, that the moon went through. So the bombardment period then left these scars of craters that can then discuss in terms of the moon's topography. That's the elevation contrasts that show high ground and lower ground, or the lower basins, which we see in dark. That the dark basins, the Maria, were once considered to be large oceans or seas. So this is where they got a lot of their names by different astronomers and observers who viewed them over the past. And we can see that the red is the higher regions, and the blues and the purples are the lower regions, lower elevation. So our focus shifts into what we view in the sky, and this would be obviously a full moon phase. Some of the terminology are going to be lunar highlands, which we will call terra, lunar lowlands, the mare, craters, mountains, and rays. Highlands are brighter than the lowlands. Highlands are lighter, lowlands are darker. And this isn't all observational. We've actually landed on the moon, if you can believe it. This is not a hoax. And maybe Jim Carrey says it best.
No way. That's crazy. We landed on the moon!
So here's just a general picture. It just shows all kinds of different craters. Some look a little different than others. Some are deeper, some are larger in terms of their radius or diameter. And the lunar surface is quite complex when you look at it in terms of all the features that are taking place that we view. And here's just a couple more pictures of that. Here we view from the lunar surface looking at Earth, how the Earth would be viewed. And here's just a picture. And I don't know which Apollo mission, but I do know it was an Apollo mission. I don't know which astronaut this is. But here we go. Terra. Nearly 85% of the lunar surface consists of the bright highlands called terra. Highlands are rough, mountainous, heavily cratered regions. The Apollo astronauts observed that the highlands are generally about 4 to 5 kilometers, or 2.5 to 3 miles, above the average lunar surface elevation, while the Maria are low-lying plains at about 1.2 to 2 miles below the average elevation. These results were confirmed in the 90s when the orbiting Clementine probe extensively mapped the lunar surface. That the moon rock olivine, this olivine basalt, is what's making up the mare, the Maria, the dark basins here are literally basalt flows. So the Maria, these are the large, dark, hole-like features on the moon that make up over, or nearly 15% of the lunar surface. Astronomers believe that they formed several billion years ago, just after the moon was created and when it still had a thin crust. Large meteoroids hit the moon with such force that they broke through the crust, and the molten lava, which was basaltic in its composition, from below filled shallow basins on the moon. The lava cooled and hardened into the large flats we see as Maria. The Maria are darker than the surrounding areas because the rock is basalt, a volcanic rock that is darker than the material making up the mountain surrounding it. Ancient astronomers thought that these dark spots of the moon were oceans, so they called them Maria, which was Latin for seas. Mountains. Mountains are especially easy to see around the outer edge of most Maria. The mountains probably formed over 4 billion years ago when most of the moon was still hot and molten. And as the material cooled, the moon shrank slightly, right, making the outer layer buckle. This pushed up rocks to form the mountain features we see today. A lack of atmosphere means that almost no erosion occurs. The moon's mountains have changed very little since they formed billions of years ago. This is unlike the Earth's mountains, which have changed greatly due to erosion, right, the water cycle. This is what makes the Earth and Moon surface features noticeably different. Craters. Craters on the moon range in size from as small as 1 inch to over 100 miles across. Craters are formed when meteoroids hit the moon. Meteoroids are large rocks traveling through space, traveling thousands of miles per hour. The energy in the meteoroid blasts a hole with raised mountain of rock on its outer edge. The crater Tycho is probably the most easily seen crater. Copernicus and Kepler are also noticeable as well from Earth. Rays. The force of the meteoroid often splashes up rock and dust that spread across the surrounding area in long, thin rays that extend away from the crater. Rays are especially visible in Tycho, where some rays reach out for more than 1,000 miles. Tycho is a relatively young crater with an estimated age of about 108 million years, based on analyses of samples of the crater ray recovered from the Apollo 17 mission and was radiometrically analyzed. It's located, if you look at the moon, you can actually see it in the kind of the southwest, in the corner of this picture here. And this is what it looks like here. The crater is sharply defined, unlike older craters that have been degraded by subsequent impacts. The interior has a high albedo that is prominent when the sun is overhead. The crater is surrounded by a distinctive ray system, forming long spokes that reach up to 1,500 kilometers. So how does a crater form? Well, so here's a picture. I'm going to kind of talk you through the terms at each of the stages. So first off, there's a contact or compression stage, that the collision site of the projectile takes place with the celestial body that generates high energy collision as kinetic energy from the moving object is imparted into the mass of which it collides with. This generates a shock wave in and around the impact site. That's what we're looking at here with these arrows. The excavation site, or excavation stage. That's where the shock wave travels into and through the celestial body, pulverizing rock and transporting it upward and outward, creating a crater-shaped site. And that's the physical structure we see here. This generally fractures cores and remelts rock at the site of collision due to the intense heat. So one is the contact or compression, and then we have the excavation. Well, the end of the excavation and the beginning of the modification stage, in some textbooks, some definitions kind of leave this out. They kind of merge this with 2 and 3, but I kind of see it as a third phase. That debris then fills in and around the crater, forming rock, the rays and the fragments that get deposited around it, as the crater is still changing. But this happens very quickly. And last but not least, the modification stage. The internal part of the crater responds to the lack of downward force and rebounds upward, creating an upward central point. Outside of the crater, walls move downward as they reposition and settle due to the new equilibrium. And here we see that the crater is fully formed. So we have this contact compression stage. This is the point of contact. We have excavation. We end excavation and build the modification, or move into modification. And then the last final settling phases into equilibrium. And I would encourage you to watch this video. It's a nice way. It kind of talks through those same stages. So geologic sequencing of lunar surface features. We can do a relative age dating of what takes place. So the lunar surface is solid rock from a molten state, right? Igneous rock. It went from a liquid phase to a solid phase. Cratering takes place from collisions of space debris. That's the cratering effect. Early in the moon's formation, basaltic lava filled in the craters. So it would have been a smooth surface. It would have been solidified. Craters continue bombarding the lunar surface. Some of them break through where basalt flows in. Secondary cratering, right? Craters within craters then occur. Notice if the basalt flow came after the surface, this now has craters. So these craters here are younger than the craters out here, right? Relative age dating tells us this. And lastly, looking at the ejecta in the rays, light-colored rays are younger than darker or gray-colored rays. Now the reason is because the solar wind actually darkens rays over time. So there's a little bit of a changing feature of the lunar surface, and that's from the solar wind of charged particles streaming through space. So what is the moon's interior or infrastructure? Well, a cross-section of the moon Like terrestrial or rocky inner planets, right? Mercury, Venus, Earth, and Mars, the moon is made up of concentric stratified layers formed by the melting and separation of magma. And we would see this small core-like feature that's synonymous or similar to that of the Earth, just on a much smaller scale. That the solid outer crust, silicate mantle, metallic core, it would be a lot less total iron, but it still has this solid iron inner core and a liquid outer core. So it's very similar to Earth and it has this partially molten region, but it's non-magnetic core, illustrating no convection in the outer core, even though this is believed to be a semi-liquid. So it's similar, but different. Composition. The chemical composition of lunar surface, measuring the regolith, right? These are the crustal rocks on the moon. So it still has a lot of silica, right? Consistent with the Earth's crust and upper mantle, or the mantle itself. So it has a lot of silica, and you'll notice that oxygen. It has a lot of oxygen, which is consistent compositionally to the Earth itself. So even the Maria has a high percentage of silicon and oxygen, right? The basalt. And the highlands clearly are the kind of the silica base that we think of Earth rocks or terrestrial rocks. So composition. Observe the amount of silicon and oxygen in the rocks found in the moon, similar to the Earth's crust and upper mantle. It's a compositional equivalent storyline that is consistent with the giant impactor theory. And lastly, just some tidbits about the Earth-Moon system. We only see the near side of the moon due to it, the moon, being tidally locked with the Earth. Therefore, we never see the far side. The moon's active side is the right side, whether waxing or waning. It is where the motion is coming from, that we're viewing the change from. The moon is situated about 5 degrees off the ecliptic plane. This is why we do not have an eclipse every time the new moon phase or the full moon phase, right? Every time we have conjunction or opposition, we do not have an eclipse. Eclipses only occur when the Earth, Moon, Sun are in syzygy, and the moon is aligned perfectly and not off at the 5-degree ecliptic plane. It has to be within the plane directly. The total area of the moon is only about 7.4% of the Earth's area. The diameter of the moon is about 3,500 kilometers compared to the Earth's about 13,000 kilometers. So the moon's about 27% of the Earth's size, just over a quarter of the size. But the moon has about 2% of the Earth's total volume. And the Earth is 81 times more massive than the moon. And this has a lot to do with the lower concentration of iron in the moon and within the moon. There you have it.